In this video, we're going to talk about work, and we're going to talk about how you can calculate work for different, different things. For example, we're going to start with the work done by friction. So when we look at friction, we know, or we should know, that friction obviously works against the motion. It works against motion, right? Because if I push something, friction is going to be pushing in the opposite direction to try to slow it down. And this is why, if I push a cart across the floor, eventually it's going to stop because there is friction, and that friction is going to push against that cart and slow it down. So we can actually calculate the work done by friction, and we're going to talk about what it is in a second. But anyway, it says here, Kevin pushes a box with 200 newtons of force. The box experiences 50 newtons of frictional resistance. Find the work done on the box by friction if Kevin pushes the box 20 meters. All right, so we have, and I'm going to draw a vector diagram here, a force diagram. We have this box. Now Kevin's going to push the box with 200 newtons of force. So I'm going to draw actually every one of my forces on here. So this is Kevin pushing. So I'll say this is Fk for Kevin, and this is 200 newtons. Now it says here the box experiences 50 newtons of frictional resistance. So hopefully you know, or you recognize, that the frictional force is going to go backwards like this, just like we did before with Newton's second law. So this is going to be F of friction. And the frictional force is going to be equal to 50 newtons. So we have two forces on here. Let's find, it says here, find the work done by friction first. So, of course, we talked about our equation for work last time. The work of, and I'm going to put a little F here for friction, just so you know I'm talking about the work of friction. The work of friction in this case is going to be, well, the equation is F times x, this is your displacement, times the cosine between them. Alright, so the force here is 50 newtons, of course. So it's going to be equal to 50 times the displacement is 20 meters times cosine of theta. Now let's talk about what theta is. I am asking for, oops, and I forgot to draw one of the vectors on here, so good thing I stopped here. We forgot the displacement vector. Again, these are force vectors, but we can draw a displacement vector as well. And we know that the box gets pushed 20 meters. So let me go this way, and it'd be like 20 meters. Ooh, almost forgot. So now we have our displacement vector here, 20 meters. Well, again, this angle is the angle between the force vector and the displacement vector. We're talking about friction. So I'm looking at the angle between this vector, the green vector, and the blue vector. And what do you think that angle is? I found in the past that sometimes people want to say, oh, well, that angle, here, I'll scoot it up just so you can see. That angle should be 0 degrees, but no, because they're opposite directions, vectors here, right? And so that angle is 180 degrees, actually. So when I put this in, I'm putting cosine of 180. Alright, I don't have my calculator, so hopefully I can do this right. It should be 1,000, right? 50 times 20 is 1,000. So what you get is, when you multiply, when you take the cosine of 180, again, make sure you're in degree mode. When you take cosine of 180, you should get negative 1. So you have 50 times 20 times negative 1, and you get negative 1,000 Newton meters. Well, this is interesting, because I told you earlier that the work done by friction, right? The work done by friction is supposed to be, well, it is a scalar. It's not a vector. So what does this negative mean? It doesn't mean direction now. It means something else. And the best way I think I can describe it is that this thing here, this negative work, kind of means that that force is working against the total result. Basically, that force is making Kevin here having to do more work than actually gets done, if you want to think about it like that. It's sort of undoing Kevin's work. It would be like if you were trying to stack up a tower of blocks, okay, and you had 20 blocks stacked up, and I come over, I take out a block right out of the middle, and half the tower falls down. Well, I've done negative work. If you had 20 blocks and I knocked over 10, I've done negative 10 blocks worth of work. And if you rebuild that back, you're going to have done 30 blocks of work total, even though there's only 20 blocks there stacked together. I think that's probably the best way to understand it. So this frictional work is working against, this friction is working against Kevin. And let me show you this mathematically too. Let's find the work done by Kevin real quick. Okay, so the work done by Kevin is going to be, again, his force, which is 200 newtons, times the displacement, times the cosine between them. Well, here, hopefully you can see that these are in the same direction, and so you'll get the cosine of 0, which, as we discussed earlier, cosine of 0 is equal to 1. So you have, that would be 4 times 10 to the third, 4,000. And you get 4,000 Newton meters of work. So Kevin actually does 4,000 units of work, 4,000 Newton meters of work. And then finally, there's one other thing we could do here. And we could find the net force, right? I mean, we could find, or sorry, not that, well, we will use the net force. We can find the net work done. So WN for the net work done. If you're looking at the net work done, there's two ways to find it. One way is, you could add up the pieces of work that are present. You have negative 1,000, you have 4,000, add those together. As you might guess, you're probably going to get 3,000 Newton meters of work. Makes sense. Here, you could also find it another way, though. You could say, okay, obviously there's another force we haven't drawn, because there's the force of friction, there's the force of Kevin, but you could combine these together to get the net force, right? And if you got the net force, you have 150 newtons for the net force. Fn for net force. 150 newtons, 200 minus 50, because again, these are vectors. This one is in the negative direction, that's positive, so you get 150. So then you have 150. So if you want to find the network, you could do this: 150 times 20 times cosine of the angle between them. Again, the angle between is our displacement vector, and our net force is 0 because there's no angle there. And then you multiply those, and hopefully you get 3,000. Yeah, you should get 3,000 Newton meters. So you see there's different ways of analyzing it. But again, when we have negative work, what we're saying is that that object or that force is actually undoing some of the work that Kevin was doing here. That friction is making Kevin work harder. Again, Kevin actually did Kevin himself did 4,000 units of work. But if you look at it, if I come back later and I'm Kevin's boss, I say, Kevin, I thought you did 4,000 units of work. I only see 3,000 newtons of work. You only moved this, you get my point. It's like he accomplished this. He attempted this, and this is how much he actually put out. This is how much was done because of friction, right? So again, I think that's where I'm going to stop the video. That's kind of the idea. Maybe I want to do, well, I'll let you do this one for practice, because I'm not 100% sure. Car traveling on a level straight road coast to stop in 250 meters. The force of friction on the car is 1,000 newtons. How much work in joules does friction do to stop the car? So here you can calculate the work done, and here, because it's stopping, that's the work done by friction. And so you can see how much work is done, and you would just take 250 times 1,000 times the angle between them. If this is the car, and that nice car, if this is the car going this way, okay, so the displacement is this way because it's coming to a stop, but the frictional force is this way. So the big key here, you're either going to pick, or hopefully you're going to pick either A or D, and the reason why A is the correct answer is because the angle between those two vectors is 180 degrees. And when you take the cosine of 180, you get -1. Great. I'm going to stop the video here. Thanks for watching.